Let's first decide what we are going to learn today. This is Quantum Search 101. Yes. So today we have certain fixed aims that we are going to cover. The first thing that we are going to learn is why quantum search is necessary, what it even is, which will be a very basic, sort of from a bird's point of view, look at the quantum search algorithm. And then we will go through a walkthrough of the quantum search process, and this will be kind of basic. The reason it will still be kind of basic is that I will be abstracting some aspects of the algorithm. The reason for that is, in the previous lecture on quantum teleportation, which was held offline, a common thread of complaint was that while the explanation was great, it seemed rushed because we were on a time constraint and we had clubbed in the implementation theory and code all together. So this time, if there is interest in the parts that I end up abstracting, we will make further videos on it. Otherwise, this is our goal for today. So first we need to sort one thing out, which is why we even need quantum search. Let us begin with someone you are extremely familiar with, and that person is you. Now assume that you are a huge introvert, and like most introverts, you have a friend who is an extreme extrovert. Your friend, like most extroverts, has invitations to an exclusive party. And by the way, this is year 5024 AD, a year where everyone knows quantum computing. And for some reason, the population of the planet has increased to 1 trillion. Exactly why you'll learn a little bit later. That's for me to exemplify why quantum search is helpful. Regardless, they have an invitation to the most exclusive party on the planet at the time. And the reason it is the most exclusive and popular party is because the entire population of 1 trillion people will be at the party. Now, as an introvert, this does sound like a huge nightmare of a process, but your friend promises you that you will always have someone to talk to. Moreover, somehow you know all of these 1 trillion people anyways. So you assume you won't have that much of a bad time. Because no matter what happens, it can't go that wrong, right? Like most things in life, you were wrong in this case too. Unfortunately, it did go that wrong. You just entered the party through the door, and like the practical person you are standing very close to the door, and you plan to talk and spend time with your friend the entire time. However, suddenly you realize your friend is lost in the crowd of 1 trillion people. That obviously fills you with dread, and your first instinct is to leave the party. But you can't do that because, firstly, you are a good friend. You will need to leave with your friend, but you don't know where the friend is. Moreover, you are a people pleaser. So, before leaving the party rudely, you want to at least talk to all of these 1 trillion people who you kind of know, and then you want to leave the party. Of course, if you try to do this with the classical search sort of way, you will have to go and talk to each of these trillion people one by one before you meet your friend, and finally, you can leave the party. Based on basic algorithmic notation, this would take O of n time, which in this case would end up taking O of 1 trillion time complexity in the worst case scenario. For some time here, and there might be connection issues, so bear with me. And if I need to repeat myself somewhere, do feel free to unmute yourself and tell me that. However, you know quantum computing because this is, after all, 5024 AD, which means you know how to complete this exact problem in the worst time complexity of 800,000, which is a huge improvement from the classical scenario. Now, it does seem that what I actually ended up doing was explain what a very basic search problem is. And you are right. But the reason we start with such a basic search problem is because search problems are extremely important in our daily lives. Moreover, search is the first place where we can see how a quantum algorithm has clear benefits and huge benefits over a classical algorithm in the practical sense. Moreover, for those of you who are actually listening to what I was saying properly, might have realized that what I ended up describing was a fancy variation of the traveling salesman problem. In fact, the quantum algorithm, the quantum search algorithm, can find a solution to the traveling salesman problem way more efficiently than the classical algorithm can. For our ease, in today's lecture, we'll not only consider the traveling salesman problem, but we'll also consider an added condition where we say we not only have to visit all the people, but we have to do that within a threshold t, which signifies the distance that we want to cover. If our solution is greater than t, that will not be a valid solution. It will only be considered valid if it is less than or equal to t. So that was a very basic run through of why we even need quantum search algorithm. That being done, now we are going to go into the next basic part of this lecture, which is what the quantum search algorithm even is. There you go. This whiteboard is a bit finicky. Yes. So what is the quantum search algorithm? What I'll explain here is again a bird's eye point of view. This essentially will enable you to tell people that I know something about the quantum search algorithm. So this is where we begin. The first thing we have is a search register. The search register contains all solutions, all possible solutions, I should say, things that could be solutions to your problem. And these solutions are represented in the form of bit strings, where X, if it is a solution in the search register, then it is represented in a combination of zeros and ones. So it could be 0, 1, 0, 1, 1, and so on. So there are many similar kinds of solutions within the search register. Of course, we are talking in terms of the quantum world. So we will be using the quantum notation, where each solution is represented in the bracket notation. We don't need to dive deep into this notation for now, in case you're not familiar with it. But I'm pretty sure that on our YouTube channel, there's already a great explanation of this notation, what it means, where it came from, and so on. For all intents and purposes, now we just know this is the quantumized way of looking at a particular solution X. Now this search register, it not only has solutions X, but it has a linear superposition of all possible solutions X. A linear superposition would mean that each solution or possible solution X would have a certain probability associated with it. So if there is a solution Xi, then there will be a probability alpha I associated with it. Of course, again, this is the quantum world, so this is how we will be representing the solution Xi. So now we have the search register with all of the X values that could be solutions to the problem. We are not sure if they are yet. What do we do with that? We feed that into something that is called the checking step, which for my own benefit, for no other particular reason, is the checking step or the C step. Okay, so what do we do in the C step? Well, this step involves introducing a qubit in its zero state, where if this solution is a valid solution, then this zero qubit is transformed into this state. Otherwise, it remains in its zero state. That is the C step at its very core. So what it does is that it goes through all the possible solutions in the search register, and then it introduces the zero qubit to that particular solution. And if it is a valid solution, it will transform the checking qubit, this zero state qubit, into one state. Otherwise, it will remain at zero state. And that is how we slowly edge towards our solution state by iteratively checking through all the intermediate states that we arrive at. So now we have a basic idea of what quantum search algorithm is trying to do. But of course, this is very basic because till now we have not really considered the biggest advantage, which is the time complexity improvement. If you look here, there is a huge improvement over here, but in this basic sort of view of quantum search algorithm, that does not become immediately evident. However, for all intents and purposes, you can now tell people you know something about the quantum search algorithm. So this is covered. Now moving on to the actual meat of this lecture, walking through this entire quantum search process in detail. Because despite the basic overview, you could ask me, no, really, what is the quantum search algorithm? And then this is what I'll tell you. We'll again start with the very basics. There is the search register with all possible solutions to our problems. Now remember, these solutions are represented in this manner, but this search register does not just have one single solution, right? It has a linear superposition of all these possible solutions to this problem. Linear superposition would imply that each solution, say x1, has a certain probability associated with it or amplitude associated with it, and x2 has a certain amplitude associated with it, and this continues up till xn, which has a certain amplitude associated with it, which means that the search register actually has a summation based on I from alpha I xi till n. This is what the search register essentially contains, a linear superposition of all possible solutions. So now that we know what the search register really contains, let's move on to the next step, which in this case, since we are looking at it in more detail, we'll have to realize that, remember how I explained how X is essentially a bit string? So this is a classical way of looking at it. When we are really looking at the quantum search algorithm, we will have to essentially quantize the solution space. And this is how we do it. We apply a Hadamard gate. Now, again, the details of the implementation of a Hadamard gate are on a separate lecture on our YouTube channel. It essentially takes a certain quantum state and then thoroughly mixes it up to produce a truly quantum state that is agnostic, which means it is often one of the most interesting quantum gates that a beginner can learn. However, again, for the purposes of this lecture and in interest of keeping things low complexity even for beginners, we will just consider what the Hadamard gate outputs when it is applied on this linear superposition of solutions in the search register. What it outputs is that it takes the xi and it gives us this term. I should also mention that in this case, the way this term is possible would also require you to assume that in the search register, all the initial solutions start from the zero state. In a real world problem, obviously all possible solutions won't be zero. They will be in different states and so on. But the good thing about quantum algorithm, the quantum search algorithm, is I can use this assumption to simplify the derivation of the formulae. And yet the derived formulae will also apply to any starting state. Okay, so that's what we are starting with, and this is what we will get on applying the Hadamard gate. Of course, this is just on one particular solution. So if I extend this to the entire search register solution space, what we are left with is, or what we really get as an output, is something that looks like this. So here, this 2 to the power n term is the size of the search space. So because it is the size of the search space, I want to make this formula look prettier. So only because of that, I'll write 2 to the power n as capital N, which will mean that our formula starts to look like this. Everything is the same. The only thing is that it will be under root capital N instead of 2 to the power n. So this is what the Hadamard gate outputs after it acts on the superposition of the solution space. Now, the good thing is that in doing this, you have been introduced to a very important concept in quantum algorithms, which is the equal superposition state, because it considers all the possible solutions. Now that we have the equal superposition state, we can finally move on to the actual checking step. I'll again represent it as the C step, because that's easier for me to write. Now we'll again revisit what we just learned, right? It introduces a special checking qubit in its zero state. This is the checking qubit. And the checking qubit remains 0 if it does not find a solution, and it becomes 1 if it finds a solution. The question is, can we write this in a prettier format? We can. We will consider a particular solution xi and the 0 checking qubit. What the checking step will really do is that it will keep the solution, or the possible solution more appropriately, unchanged, but this 0 qubit can become either 0 or 1 based on whether the solution is valid or not. That we will represent as the s variable, which can be 0 or 1. But this is not entirely correct. This s variable actually depends on the solution. If the solution is correct, it will be 1. If it is not, then it will be 0. So we will actually represent it as a function of x instead of just a variable. So now this whole thing represents, or this whole thing can be 0 or 1 depending on x. Now, obviously, the first question for beginners might be that how does it even convert this initial state to this final state? And that is a valid question. However, this is the first abstraction. Okay, there is some sort of problem there. Yeah. This is the first abstraction that I want to be introducing here. This step is not really magic. It is a combination of quantum gates and other sorts of quantum algorithms, not necessarily algorithms, but quantum gates and steps that would transform this into this. But that is beyond this particular lecture. If you're interested in it, you can inform us and we will make a video breaking down the entire process of how this conversion happens. This sort of abstract. So what the Hadamard gate does is, you might have seen me writing this briefly, is that if it has a qubit in the 0 state, I'll actually write this in a fresh position so that it is more understandable. And this is the preliminary knowledge, so I won't necessarily put it in this flowchart, is that the Hadamard gate does the follows. If you apply a qubit in its 0 state to the Hadamard gate, then it outputs a mixture of that qubit's initial state to produce uh, this value. Meanwhile, if you apply a qubit in its 1 state to the Hadamard gate, then it happens to produce this value, which is why in this example, remember how I said we assume that all the solutions are in their 0 state just for the ease of explanation. That is why when we are finally deriving the Hadamard gate, the equal superposition state, it is easy to derive this formula because we are only considering it in its 0 state. So this is the only formula we need to keep in mind. We don't necessarily need to deal with the subtraction that the 1 state introduces. That is the Hadamard gate in just a simple overview. Moving on to the actual checking step, I think I left it off where we apply the checking qubit and then we get this mixture of states, and that we will be abstracting away how this checking step actually transforms this state into this state. In quantum algorithm explanations, this step is pretty much called the oracle step, which means that we assume that this is what this step does, not through magic, but through an implementation that might be more complex within the purview of the current lecture. So now we know how the checking happens on the particular solutions and how we next need to move into our final solution state. I will be representing the solution state with this S notation. Do not please confuse this with the search state. This is the solution state. So keeping that in mind, I will be explaining the derivation of the solution state in the easiest way that I found, which was a geographical way instead of the linear algebraic traditional way. And this is what I mean. It will be way more intuitive as well. So we will consider our initial state to be the equal superposition state. Let's see if I can get the correct tools in time. Okay, that we don't need an arrow. Yes, there you go. So we have our solution state and we have our initial global superposition state. Let's see, I'll just increase the thickness in so that it is more visible to everyone. There you go. This is the solution state and this is the equal superposition state. Now our job is to swing around from this state where we currently are to this solution state. But unfortunately, it's not that simple because if we could just go from this vector to this vector, then that means we know where this vector is. And if we know what the solution is, then there's no point in applying a search algorithm. So it stands to reason that in trying to get from here to the solution state, we will end up with an intermediate state. Let's call this intermediate state psi. When we have this intermediate state, we are hoping that we went closer to the solution state. So we essentially went from the initial state to this intermediate state, and we are trying to go from here to the solution state. The only problem is, again, we don't know where the solution state is. So instead of randomly shooting arrows in the dark and trying to get here or there, because we don't know where the solution state is, we could end up with our intermediate state here or here in trying to estimate the position of the solution state. So instead of trying to do all of that, let's do something that is kind of fun. Let us reflect around the solution vector. If we reflect around the solution vector, then we will end up with the psi state in its reflected format, which is what I am denoting as psi r. And according to the basic laws of reflection, the angle of incidence is equal to the angle of reflection, which I will be denoting as theta. That seemed kind of fun. We swung around from here to here, then we reflected around a vector, and that sort of reminds me of Tarzan swinging around in the forest. So you know what we'll do? We'll actually do that again. The vector we seem to not be using right now is the equal superposition vector. So let us reflect around this equal superposition vector. We will take the vector that has already been reflected once and reflect around the equal superposition vector. In doing so, before that, I just need to clarify certain angle assumptions. First things first, the solution state and the equal superposition state, they might look like they are at 90 degrees, but they are not. They are at a slight deviation from 90 degrees, and that slight deviation will be represented as angle delta. Just assume that these lines are all connected at a common origin. So I will be representing that with some different color so that it is obvious that this is the deviation. This is 90 degrees, and solution state and equal superposition state are deviated from the 90-degree orthogonal state only by delta. So if we want to reflect this reflected intermediate state around the equal superposition state, then let us draw where we think it will end up at. Let's assume that this angle is phi. So if we reflect around the equal superposition state, I think we'll end up somewhere around here. Let's use the black color again. Somewhere here, I will again try to deal with the finicky whiteboard. Let's say it will end up somewhere around here. And what is this angle? Well, we reflected around theta plus phi. So this angle will be 2 theta plus phi. Well, that seemed pretty simple. Now, based on, again, kind of elementary linear geometrical knowledge, two reflections would imply one single rotation. The exact definitions are not necessary in this case, but what that means is that this double rotated intermediate state, I can consider that it has just been rotated from the first original intermediate state instead of being doubly reflected. Is the same thing really. So this is the doubly reflected state denoted by psi r r. So what we now need to consider is that if it was the rotated state of the original state, then by how much did we rotate the original state? So that's a good question. Let's see the difference between the rotated state and the original state. It is very simple addition. Let's use a different color here. It is at a distance of or an angle of a rotation of 2 theta plus phi. That implies that this angle between the original intermediate state and the rotated intermediate state is 2 theta plus 2 phi. What is this 2 theta plus 2 phi? We are slowly getting closer to it. This is some really elementary linear algebra that we are now nearing. Let us represent it in this manner. Remember how I said the solution state and the equal superposition state would be at 90 degrees if not for the deviation? We will now use that. Theta plus phi would have been equal to 90 degrees represented in radians if not for the slight deviation in delta. I think we can simplify it again with very basic performance of my mathematical prowess. I think it would be pi by 2 minus theta minus phi. Again, another step over here so that we get 2 delta is equal to pi minus theta minus phi. Oh, there will be a 2 coefficient over there to deal with that. Wouldn't it be interesting if I put 2 theta on the left hand side and 2 phi on the left hand side? We keep pi where it was and we bring 2 delta on the right hand side. The left hand side is now looking very interesting because this is the value that we were looking for initially. This means that we have rotated the original intermediate state by pi minus 2 delta angle. There is something else that I want you to consider. I want you to realize that I'm going to make a bold assumption here. The bold assumption that I'm going to make is that psi and the rotated vector, intermediate vector psi, are opposite to each other. And the way I'll justify what I just said is by showing you this. Consider two orthogonal axes, x and y, and a vector in there which is at a certain angle. But do remember that these are orthogonal axes. So if I reflect this, which is say at angle, I don't want to say theta again, so I will say m because I like that letter. It is at an angle m from the y-axis, which means if I reflect it around the y-axis, the reflected vector will also be at an angle m, even if it does not visually look so. So if I take this singly reflected vector and try to reflect it again at x, which is what we were, something similar to what we were just doing with the equal superposition state, if we try to reflect it again, then we end up with something that will be reflected by m plus 90 degrees. I will extend the axis in order to make it more obvious. Yes, so this vector gets reflected at m plus 90 degrees or 90 degrees plus m. And so clearly these two vectors are opposite to each other. However, you might have noticed that I was a bit dishonest about something because these two axes are orthogonal to each other. Meanwhile, we know very well that our solution state and equal superposition state are not orthogonal to each other. They would have been, but there's a slight deviation of 90 degrees, which means that this solution state and this this intermediate state and this rotated intermediate state would have been completely opposite to each other, but they are not. They are deviated by a slight amount. And that is what is represented by this right hand side. It would have been a pi amount of rotation, but there is a slight deviation of 2 delta terms. So now that we have understood both the left hand side and the right hand side of this equation, let's move on to understanding how this helps us, how all of these swinging around vectors really helped us. I'm sorry, I think I was disconnected for a bit there. Yes. So we are left with this, which means this is the rotation that we did. Based on quantum algorithms, really, we are kind of careless about global phase factors. So, for example, we can ignore, in a way, this pi minus term and be left with a rotation of 2 delta. We can't ignore it randomly, obviously. That means that instead of considering this vector, we will be considering its opposite state, which would look something like this vector. Where is it? There you go. I will represent it much more neatly in a bit. But keep in mind, the only thing that happened over here is that the intermediate state was psi. We reflected it around the solution state once, and then we reflected it again around the equal superposition state to get a rotated intermediate state. Now the rotated intermediate state is at a really awkward angle. So we remove the pi minus term over here and we consider its opposite vector, that is also the rotated vector, but now it is 2 delta instead of pi minus 2 delta. If I just represent everything that I did over there neatly over here so that you can see what is actually happening or what I am getting at. Nope, that's not what I want to happen. There you go, that is the equal superposition state. There is our intermediate state, and there is our doubly reflected or rotated intermediate state. This is our solution state. This is our equal superposition state. The intermediate state that we swung around to, and this is our doubly rotated intermediate state. So what we ended up doing is that while we couldn't have swung around directly to the solution state, we first swung around to, this is not, wait, there is a slight mistake in notation here. Yes, there you go. This is the equal superposition state. Instead of swinging around directly to the solution state, we first swung around to an intermediate state, and closer to the solution state than we initially were. We are slowly inching closer to the solution state every time we repeat that operation that we just talked about. So what do we do with this doubly reflected intermediate state? Well, we reflect it again against the solution state. Then we reflect that against the equal superposition state. And then we remove the pi minus global phase factors because we can, and get another vector which is even closer to the solution state. So you can clearly see how if we keep iterating this process, we will slowly inch closer and closer to our solution state. When I say this, the obvious question here is, how many times do I need to repeat this process? Because at the end of the day, that is what will create the most delay in computation. You don't want to repeat it 1 trillion times. So how does quantum search help? Well, ideally speaking, if we could just rotate directly from the equal superposition state to the solution state, our problem would be over. So that would mean we would have to rotate ideally by 90 degrees minus delta. Why 90 degrees minus delta? If we rotate by 90 degrees, then we will actually overshoot the solution state and end up somewhere else. Remember, there is an initial deviation of delta. So ideally, we wanted to rotate to a position which is pi by 2 minus delta, but we can't. So what we do is that we repeat the steps that I previously mentioned. How many times do we repeat it? We repeated the following number of times. I'll change my ink to black because this is more of a formal formula we are edging towards. We want to repeat it, the total angle by which we want to end up divided by how much rotation are we ending up at each step, the total angle and the angle we are rotating by at each step. That will give us the number of times we want to rotate. So that will number of times that we want to iterate this whole algorithm. If I can simplify this again with whatever limited mathematical knowledge I think I can apply here, I think it will start to look something like this. And I think I can simplify this to pi by 4 delta minus 1 by 2. That actually looks kind of pretty. And if some of the abstractions that I mentioned were not present, then you would realize that delta, when you are assuming all the solutions initially are at zero state in the search register, would be somewhat equal to 1 by root n. If you realize that, which we won't, we will again treat it as an abstraction just for now, just for today's lecture where we are understanding quantum search, then you will realize this already pretty formula can actually be even more prettified, and what we will be left with is that the upper bound of the number of times we need to repeat this algorithm will be equal to pi by 4 term will remain the same, root n, that's not a good n, plus 1. This is the upper bound of the number of times you will need to repeat that whole reflecting process. And you can see that this means that our time complexity would be O of root n instead of On, which is a huge improvement as you previously saw. So there you have it. If I sum it up quickly before I end this lecture, we started with a search register. That search register had all the possible solutions to this problem in a superimposed state. And this is what that looked like. We applied the Hadamard gate to it because we wanted them in a quantized, or I should say a quantumized state of solution so that it is not classical computation anymore. And once we do that, we actually end up with our initial state, that is the equal superposition state. Once we get our equal superposition state, we realize we have to get to our solution state. So when we realize that, the first thing we do is that we know we will end up at an intermediate state. We reflect that intermediate state twice around the solution state and the equal superposition state to end up with the rotated intermediate state. That rotated intermediate state is closer to the solution state than we were initially by 2 delta. And because of that, now we are inching closer and closer to the solution state. We will check if the intermediate states are the solution through the checking step. We can see here that they are not, but when you are actually using this algorithm, you won't know. So that's why you'll have to use the C step there too. Once you keep checking and finding out if they are the solution state or not, in this case it won't be, you repeat the above step, you again reflect around the solution state, then around the equal superposition state, and every time you do that you inch closer, you apply the checking step, and you repeat this whole process. How many times? You repeat this pi by 4 delta minus half times, which ends up to a time complexity of O root of n, which is a huge improvement over O root of n. And that is a very basic summary, but still we delved into some of the more intricate implementations and ideas behind the quantum search algorithm. Thank you everyone for joining. Really glad to have you all over here. The recording for this lecture would actually be available on our YouTube channel in a couple of days, as well the resources that I used also be available on our GitHub account, which you can visit, or everything is linked on our Instagram bio, and hopefully start the repositories as well. It really motivates us. So thank you everyone. I will end this meeting if it's all right with everyone.
Yeah, we'll just save the downloading first for the recording.